Okay, so here's the problem. Notice that I have changed somewhat from what has been happening so far, and I'm looking at a series of counts. These are not really time series, so to speak. These are independent observations. Now, you hear about data smoothing, frequentist and data analysis. Everybody does that. What is it for? How does a Bayesian look at data smoothing? How do you get out of that? Why should you smooth the data? What's the point? Let's look at a couple of examples to find out what the real idea is. Okay, suppose these counts actually stand for, let's say, traffic accidents, a bunch of accidents, and obviously you want to know what happens at a future time. How are you going to do that? Or it could be that there's a production process and the counts stand for the number of defectives detected in a sampling scheme. And obviously you want to know what the proportion of defectives is. Okay, now fine, if that's what you want to do, that's what you are going to do, isn't it? But how does data smoothing help? What is data smoothing? Well, the idea is that you want to know more about not the counts themselves, because they don't really tell you much, but you want to know more about the underlying process. Presumably, the process is well related to what you get, that namely the counts, and a good understanding of that will tell you how to do these inferences. So in that context, if you take these counts and smooth them, probably that will allow you to go down deep and look at the structure. So that's precisely what data smoothing is all about. Okay, now how does a Bayesian look at it? Well, now there are various different approaches available for data smoothing. I'll begin with the smoothing for measurement models, and this is not what I'm discussing here, but there's extensive literature available for that, so let's look at that. So if you have bivariate data like this, X is covariate and Y is actually what is of interest, then in the measurement model context one writes down a model like this. Y is expectation of Y given X plus an error. And in that the model, what G stands for is the actual underlying smooth regression function. Okay, so data smoothing actually in that context tries to get the regression function. And once you have the regression function, you can do a prediction, you can do inference, you can do all sorts of things. Okay. And there are various Bayesian models available for providing the smoothness structure on the regression function. This need not be linear regression. You see, the regression function can be anything. So you may have some information about the smoothness of the regression function, not necessarily that being linear, but something else. And in that case, how are you going to put that into the model? That's the question. So there are the spline type models that began with Waba's work, and at the same time there is the work by O'Hagan on curve fitting, and and some other kind of work, namely the stochastic trend models of Kitagawa, Ghosh, and so on and so forth, and then the dynamic linear model approach of Harrison, West, and so on and so forth. And of late, what is hot is this Fourier series approach, or the wavelets approach. What they try to do is expand this regression function using Fourier series wavelets. Well, in spline type models, it's just expanding using a Taylor series kind of thing, and then you, if necessary, put a prior on the coefficients, extending the idea of putting prior on the regression coefficients. Okay, so that's what is available for measurement model regression situations. Unfortunately, that's not the situation that we have. Why is that? That's because we can't, well, we can write down, of course, y equals g of x plus epsilon, g being the regression and epsilon being the error, but this is not the situation as what we have in the measurement error model, because the noise is not independent of the signal. Both have the same parameter. We'll see that in a minute. So you can't quite do that. That approach is not quite proper here. Okay, so what is to be done? All right, so let's go back to the problem. We have a series of counts. So remember, this is not a time series in the sense of the time series models. These are independent observations. But I do have a time series in the sense that these are across time. Okay, but given the parameter, these are independent counts. So in a sense, this is not an analysis of time series, but later on I'll show you where I'm using time series modeling. Actually, time series modeling for the Bayesian inputs to solve the statistical problem. Okay, so that's going in the reverse. If you recall the lectures that we had on analyzing time series, real time series. Okay, all right. Okay, so what we want to do is either make some predictions or make some inferences. So if tau is some future time or time at which some observation is missing, then n tau is the quantity of interest. So we have seen n1, n2, n3 like that, maybe up to n capital T, observations being little n1, little n2 and so on. And I want to know what the situation is going to be like at time tau. Okay, so all that a Bayesian needs to do is compute n cap tau, which is of course the expectation of n tau given the data that we have seen so far. Okay, so it's a very simple answer, but how do you actually compute that? Okay, so here's my modeling. I already said it's a series of Poisson counts. So let's suppose that lambda t is the mean of this Poisson. So I'm not assuming that lambda is a constant. Lambda actually, it can actually vary over time. So when we say lambda is the mean of Poisson t, it simply means this. If you know the behavior of lambda as a function, then expectation of nt given this function is just lambda at t. Okay. So what I want to do is providing a basis for data smoothing, and that will be assuming that this function lambda is smooth. So a Bayesian has to model that. What do you mean by a smooth function? How smooth is this lambda? Okay. And if that input is given, then presumably a data smoothing based on that will allow us to understand what this lambda is really like once we finish this data smoothing, and then we can make all future inferences, predictions, so on and so forth. So that's the basic idea. All right, so this is where I use the hierarchical Bayesian approach. So I'll have a first stage model for the parameters, namely of course this lambda here as a function. And so that means there will be some hyperparameters which will provide a model for lambda given these hyperparameters. And then I'll eventually need a prior on these hyperparameters to handle the entire situation. Okay, so I'll make this transformation. I'll look at the logarithm of the intensity function lambda instead of lambda itself. So that means of course the expectation can be written like that. And now I'm going to incorporate this idea of smoothness. Lambda is smooth, so that means nu is smooth. Okay. So that means if you take two time points t and tau, you can say something about the dependence between those two. Function is smooth, so it can't jump arbitrarily. Okay, so assume that this nu 0, a constant, is the mean level of the series, and if you take any tau less than t, you can write it like that. Nu t minus nu 0 is a correlation which will involve, in general, both t and tau. Nu at tau minus, of course, this mean, plus something which is uncorrelated with nu tau. Now, there is nothing very complicated about this. This is standard. See, if you take two random variables x1 and x2, both having mean 0, that's what I do by subtracting of nu 0, and variance 1, then if the correlation between those two is rho, I can write this down. x2 is rho x1 plus square root 1 minus rho square times something which is actually uncorrelated with x1. Because notice that now variance of u is 1, that doesn't really matter, but look at the correlation between x1 and u, that's just 0. So you can always decompose the quantity like this. Okay. Now this gives me the basis for providing the smoothness of mu. Let's see how. Well, this is just one approach. You can do it in a number of different ways. Okay, so let me put this back. So I have written this down. Nu t minus nu 0 is rho, which can involve both t and tau, times nu tau minus nu 0 plus something which is uncorrelated with nu tau. Okay? All right. So now I take a simple stationary AR1 process to provide this smoothness input. So I take rho t minus 1 to be a constant a, and I take that remainder u to be an AR1 process. Okay, so 1 minus a square root of that times u t tau is just this sum, partial sum, where the epsilons, these have nothing to do with the measurement error model that we looked at earlier. This is just a sequence of normals, bidirectional sequence that's needed because this is an AR process, and that's what the structure that I have for u. Okay, see epsilon r's given some hyperparameters delta square and a, delta square being the variance, well, in some sense, and a is the correlation that I wrote down earlier. It's just normal with mean 0 and this variance. Okay, so that actually tells me that the dependence between nu at time t and nu at time tau is like this. Nu t minus nu 0 is a power of a times nu tau minus nu 0 plus something which can be written as a partial sum of these normals. Okay, and similarly you can do it for any tau greater than t, for example. Okay, so why am I doing this? I'm doing this precisely for providing a smoothness, Bayesian smoothness input for this intensity function lambda. I have this log of intensity function given by nu. For that I have given this structure, and that translates into a similar structure for lambda, and that gives me a first stage model for lambda. Okay. Right. So once that's given, I want to go ahead and find the estimates for n tau, for any tau, and that of course is going to be just the conditional expectation n tau given the data, and a measure of error, which will be just the square root of the posterior variance. So that's what I want to do. Okay. Now there isn't too much to say except how to do the computation. So I'll introduce a few notations. So my n vector is the vector of counts, the real data that I have, and nu is the vector of intensity at these points. So notice that ni relates to nu I directly, but because of the smoothness condition, the different ni's will say something about the different nu i's also, and that's the basis for making any inference. Okay. Right. So I want the estimate for n tau given the data, right? And that's just expectation of n tau given the vector n. But I'm going to write this as an iterated expectation. You'll see in a minute why I do that. Given nu tau, now notice that n1, n2, n3, all these are assumed to be independent counts given the parameter nu. So the inside expectation just turns out to be e to the nu tau, lambda at tau. So the inside expectation is very simple. So I just have to find expectation of e to the nu tau given the data. Now I'm going to introduce the hyperparameters also along with the nu vector. So again an iterated expectation. Okay. Now I'll show pretty soon that this can be simplified a lot, because conditional expectation usually means that well, computation of these expectations usually is high dimensional integral. I want to avoid that at least in some context, so I'll tell you how that can be simplified. And similarly, the measure of error that I want, standard deviation, I wrote SD, square root of the posterior variance, that also can be written as an iterated expectation, difference of two of those. So what one sees is this. See, here I have expectation of e to the nu tau given certain parameters, and down here I have expectation of e to the nu tau plus e to the nu tau, e to the twice nu tau plus e to the nu tau. So again, so if you split that into two parts, what you see is, what we really want is, of course, a simple formula, if possible. The inside expectation, that is just expectation of e to the k nu tau given the nu vector nu1, nu2, nu3, nu0. What's that? That's the mean of the series. Delta square, the hyperparameter which is the variance, and the other hyperparameter a, that's just the correlation between t and t minus 1. Okay, the nu t and nu t minus 1. Okay. Now, what is this? This is just the moment generating function of nu tau given these parameters. See? So at least in some situations I can easily find this, and that's what I'm going to exploit here. Now, from the AR1 model, notice that the joint distribution of nu tau and the nu vector given these hyperparameters is simply a multivariate normal, where this sigma matrix is, because of the AR1 structure, it's like this. It's the standard matrix that you encounter in AR processes. Okay. All right. So what does that mean? So remember what we want. We want the conditional distribution of nu tau given nu, nu0, delta square and a. Because of this structure, it's a univariate normal. From a multivariate normal, you just derive this univariate normal, and we want the moment generating function of that. That will give, at any k, that will give this expectation. So with this structure, this inside expectation, what inside expectation? Well, this inside expectation here and this inside expectation here can be simplified, because they are just the MGF evaluated at certain points. Okay. Right. Now, the moment generating function for the normal distribution is very well known. It's just the exponential of the mean plus, well, that's where it is. Variance appears like that. So all that we need to do now is, so inside expectation can be analytically written down, so that we only have the outside expectation left. That has to be found with respect to the posterior distribution given the data. That will come to in a minute. So now notice that the inside quantity is a function of the new vector, which relates directly to the data, and the hyperparameters mu 0 and delta square, and also the correlation coefficient A, which appears in these components of the covariance matrix. Okay. The other quantity that we need to find the precision, estimation error, is of course the variance that requires the second posterior moment, and for that, well, the MGF has to be computed at 2 points, k equal to 1 and 2. So we write that down, and again notice that we have just the outside expectation left. Okay. All right. So that's what the computation involves, given the smoothness structure involving the AR process. How does one do the computation then? Well, for that we need the posterior distribution of the new vector, nu1, nu2, nu capital T, the hyperparameters mu 0, delta square, and A, given the data. Right? Okay. We already have the prior on the new vector given mu 0, delta square, and A coming from the AR1 process. So that part is there. So all that we need now is the prior on the hyperparameters mu 0, delta square, A. So that's the second stage prior, which completes the hierarchical model. That's done. We can go ahead and do the computation. So just for this example here, I have assumed this particular structure for the second stage. I won't worry too much about that. Of course, one should worry a little bit. So I assume that mu 0 again is normal, delta square is gamma, or actually inverse of delta square is gamma, and A square is beta with certain constants alpha and beta. Now this is the second stage prior, and people who have worked with hierarchical models have noticed, this is discussed in Berger's book again, that one has to worry a great deal about the first stage prior. Of course, one has to worry about the second stage and the higher stages also, but in hierarchical models there is always some robustness with respect to the higher stages. So the precision of the prior at the higher stages is not that important. You can get away with some imprecision. Okay, so what I really mean is, even if you vary these prior somewhat, you won't end up getting vastly different answers. Okay, that's the idea behind robustness here, prior robustness. Okay, so I have assumed that prior, so that completes the prior specification. The first and second stage completes everything, so I just have to do the computation. Okay, now the computation can be done directly, there is no problem with that. Okay, so for that, of course, I have never written down the likelihood function explicitly. Here it is. You have independent Poisson count, so the likelihood for the new vector, well, the data can only say something about the intensity at those points, right? So, but remember how lambda and nu relate. Nu t is just the log of lambda t. Okay, so the likelihood function is actually for the lambda vector, lambda 1, lambda 2 of lambda t, but of course nu is just the log of that. So that's the likelihood function in terms of the nus. Okay, so what is the posterior distribution of the parameters, first stage and second stage? It's just the product of the likelihood function and the prior that we just discussed, properly normalized. Okay, where m is the marginal, which means you need to integrate out all the parameters. Once you have that,
the Bayesian computation, which is of course finding the expectation of n tau at any tau given the data, is just finding expectations of this kind. We need two expectations. One is expectation of nu 0 plus something, and again expectation of e to the twice nu 0 plus something. Okay, so but the expectations are with respect to this posterior distribution. Likelihood times the prior that we just mentioned, properly normalized. Okay, so that's what needs to be done. Quite straightforward. So these days Bayesian computations are not considered too difficult. There are various methods available. One can do a straightforward Monte Carlo importance sampling. You can done for any g in addition, instead of the two gi's that we just looked at, e to the nu 0 plus something, e to the twice nu 0 plus something, so on. Anyway, what needs to be done is, well, you write down the expectation carefully as the ratio of two integrals, and then you generate observations from a certain distribution, apply the law of large numbers, making sure that the convergence is there and so on and so forth, and then you have the Monte Carlo importance sampling estimate for what you want to compute. Okay, so if you want to find the posterior expectation of g with respect to the posterior distribution that we just wrote down, then it's the ratio of these two things. In the numerator you have g, which is absent in the denominator because the denominator is just the normalization. So you call the parameter vectors theta, in which case you have g of theta, f theta sub n, because the data is there somewhere, and then you have pi theta d theta. In the denominator you have just f times pi. So if you generate, okay, the simplest thing to do is to generate directly from pi. It's possible in this case, not always possible, but here in this particular example it is possible. If you generate observation from there, then notice that if you look at this ratio of averages and apply the law of large numbers, then it will converge to what you want to do. Okay, the expectation. So that's something that can be done. It's quite straightforward and it does work. It does work unless the counts ni are large and you have too many of them. Okay. In other situations, if ni are really large, then this is going to take a long time and the convergence is slow. It's not very efficient. Okay. So to handle such situations, in this particular example, we have modified or adopted the what's called the Laplace approximation or the saddle point approximation, originally given by Lindley, but later on for specific situations modified by Tierney and Cadin, and of course further modified by Tierney, Cadin and Cass and so on and so forth. Okay. Now that can be used here, and that simplifies the problem substantially. And even when ni are large and you have huge data sets, you can still go through with everything and get reasonably good, or actually very accurate estimates. Okay. So what that involves is the following, or at least in our modification. I'm going to approximate the likelihood. I have the likelihood there, and notice that there I have e to the nu I and all those things, which makes the likelihood somewhat complicated. What I'm going to do is subtract log of ni from this nu I. That's what I have done. I have e to the nu I, the first part, e to the minus summation e to the nu I have. Instead write it as e to the minus summation e to the nu I minus log ni. Of course, you have to compensate for it, so multiply that back. And then similarly, the second part, you have e to the summation ni nu I e to the summation ni nu I minus log ni. Of course, you have to multiply it back, but that just depends on ni, so it doesn't matter because after all I have written proportionality here. Now notice that the formula then changes to simply this, e to the minus summation ni times, because e to the log ni is just ni, e to the nu star I minus nu star I. What is nu star? Nu star is just nu minus log. Okay. Now I'm going to expand this e to the nu star in a Taylor series around 0. Okay. I have that here. Okay, so I have e to the minus summation ni e to the nu star I minus nu star I. Well, expand e to the nu star I. 1 plus x square over 2 and so on and so forth. Throughout the higher order terms, that gives you the approximation, and nu star, recall what nu star is, just nu minus log of the counts. And now notice that this is just the density of a multivariate normal with mean vector, which is the vector of logs of counts, and the covariance matrix of course is 1 over the counts. Okay, so now the likelihood is well behaved, and this is not something really that you haven't seen. This is just the normal approximation to the Poisson. Okay, and that's valid for only large counts. Okay, so now what do we have? Well, we have the normal prior, multivariate normal prior for the nu vector given the hyperparameters, and we have the normal model for nu approximate. Combine those two. The posterior for nu given the hyperparameters and the data is simply a multivariate normal. Okay. How does this help? Well, recall what we want to do. We want to find the expectation of n tau given the counts, vector of counts for any tau, and that we wrote down like this: expectation of e to the nu 0 plus things. Okay. Now I'm going to separate out the hyperparameters and nu, the first stage parameter. Okay. So pull that out. Now this part I can simplify. Why? Because that's again the moment generating function of nu evaluated a certain quantity. Okay. Now given the normal structure, I can explicitly write that down. Okay. Now what that gives me is the following: if I want the posterior quantity, I just have to find an expectation with respect to this quantity, the posterior of only the hyperparameters given the data. Now, how is this different, or how does this make any difference? Remember or recall what we said. What we want is this: finding the expectations of things like this with respect to this posterior distribution. Now, this has how many parameters here? The nu vector has as many components as the data set